Hi, welcome back. This is now 5.6. Indeterminate forms of L'Hopital's rule. We'll need to be able to do these operations in order to do improper integrals in 8.8. That's why we typically introduce it now as opposed to in Calc 1. You've kind of touched on the topic in Calc 1, so let's just do a little bit of a limit review before we get in too deep. And we'll begin with the most basic type of limit. So if you're dealing with a continuous function, all you need to do is substitute the value, the x value that you're approaching into the expression. Okay, so to figure out this limit, you just take the 4 and you dump it into this function wherever you see x, and you'll have 16 minus 3, which is 13. Okay, so that's the easiest type of limit, and this is generally how you approach all limits. You try to just substitute in the number into the function and hope for the best, right? And of course, that's not always going to work. And the first example, which you've seen in Calc 1, is this 1 over something, right? So maybe x squared. And in my class, I always refer to these as L over infinity forms. So the L just represents some number. And then the denominator, if you just think about where x squared is going as the x values go to infinity, the x squared function will just go up and up and up and up. In other words, it will go to infinity. Okay, so you're dealing with some number that is fixed all over something that's getting really, really, really big. So ultimately, the end limit of that process will be 0. Okay, you can also look at it in terms of a table if you don't like the graph, but you should be able to do these without having to do a table or a graph or anything, just based off of the form. Anyways, you know, you're taking values of x going to infinity, like 10, 100, 1,000, and you're putting it into this 1 over x squared, so you get 1 over 10 squared, which is 1 over 100, which is 0.10 hundredths, you know. So this would be 1 over 100 squared. So, you know, 1 divided by 100 squared equals 0.0001. And you're getting closer and closer to what? Well, to 0, right? So the limit is equal to 0. Okay. So that was kind of one of the first different forms we saw. Another different form we see is the L over 0 forms. So this is a limit as we approach 3 from the right of 1 all over 3 minus x. So in the numerator, we just have some number, and then the denominator, it's like we're dividing by 0. So in these cases, it'll either go to positive infinity or negative infinity, depending on the approach numbers. So I generally will do kind of a, well, first I'll draw the number line. Okay, so here's 3. I'm coming in from the right, and then I do a test value. Okay, so I'm going to plug in 3.1 into this expression, and I'll have 1 all over 3 minus 3.1, which is going to be a positive over a negative. So at the end of the day, it's a negative number, so it's going to go to negative infinity. Okay, so far we have two forms. The L over infinity form is going to be 0, and then the L over 0 form is going to be negative infinity. You can go through and kind of do an analysis with all of these different kind of forms. Another example of a form, the limit as x goes to infinity of x e to the x. So in that case, the x portion here is going to infinity, and then this e to the x portion, as you put in values going to infinity, like 10, 100, 1,000, that will also go to infinity. And so this form is basically infinity times infinity, and when that happens, the result is just going to be infinity. So if you did a table, it's like you would have 10 times 10, 10 times 100 times 100, 1,000 times 1,000. and the numbers are just getting bigger and bigger and bigger and going off to infinity. Okay, so there's a lot of forms like that. There's like infinity times negative infinity. That'll just be negative infinity. We should be able to handle polynomial type forms. So, for example, the limit as x goes to negative infinity of 3x cubed minus 2x plus 1. You can look at the shape of the curve. So if it's an odd shaped, if it has an odd degree, it's going to have either this shape where it does something maybe funny in the beginning and then goes in the middle and then goes out like that, or it's going to have this shape and then go down like that, right? So in the first case, it's if the leading coefficient is greater than 0. In the second case, it happens when the leading coefficient is less than 0. So this problem, the leading coefficient is positive, so it's the first case. And the x values were going to negative infinity. So we're actually going in this direction. And the limit is telling you where the y values are going, what's happening to the y as the x goes here. So in that direction, the y values are going to negative infinity. Okay, so what else did we see? Rational functions. So for example, the limit as x goes to infinity of some polynomial over some other polynomial. And what's happening here? So the numerator polynomial has even degree, so it's going to have some shape like this. It's a polynomial in particular, so we know kind of what it's going to look like. And so as x goes to infinity in this direction, the numerator y values are going to go to infinity. And likewise in the denominator, it has the same positive leading coefficient. Of course, if leading coefficient's positive, it's pointing up. If it's negative, it'll point down. So it's both infinity. So this is called an indeterminate form. It's infinity over infinity. And in Calc 1, you're probably told to divide top and bottom by the highest degree term. So 3x squared. It turns out there's a much quicker method to approaching this problem, and that's just to consider the limit of the high degree terms. Okay, it's equivalent to what you were taught in Calc 1, and it's much quicker. After a while, you can just look at it and say, oh, the limit's 2/3, right? So here the x's cancel out, and you get the limit of a constant, which is just a constant. Okay, so that's the case when the degrees are the same. When the degree of the numerator is less than the degree of the denominator, that will go to 0. But you could still approach it in the same way. In other words, you can circle the high degree terms and then consider that limit, and you'll get the correct answer. Right, so this would be 3x cubed over 5x to the 4th, which would be the limit of 3, well, the x cubed will cancel with the x to the 4th, leaving one factor of x in the denominator. And then this critter is L over infinity, which will go to 0. Okay. The only other case was when the degree of the numerator exceeded the degree of the denominator. In that case, we have a limit as x goes to infinity of something like 5x to the 5th plus 2x minus 1 all over 3x cubed plus 2, let's say 2x to the 4th plus 1. You want to be a little careful if they don't put the terms in descending order of degree. So for this problem, you would have to circle the second term in the denominator and consider the limit of 5x to the 5th all over 2x to the 4th. Okay, so this will be the limit of 5x over 2, which is basically just a positive slope function going through the origin, so up 5 over 2, up 5 over 2, up 5 over 2. And as x goes to infinity, y values will also go to infinity. Okay, so these types are always going to be like the ratio of leading coefficients, or 0, or infinity, or negative infinity. Okay. Okay, and each type was considered what's called indeterminate. So that's what we want to investigate in particular in this section. It's these indeterminate forms. So you already have a little experience with them from Calc 1, and in Calc 1 they gave you methods for dealing with it, like the method I was just showing you there in the previous 3 examples. There were other methods too, though, that might be a little bit more familiar to you. Let's investigate some of those. So the first maybe indeterminate form that you probably saw would have been the 0 over 0 forms. So in those cases, like problem 3 in our homework, you have the limit as x goes to some number. And then I have x squared minus 5x minus 50 all over x minus 10. Okay, so what I'm going to do here is factor the numerator. Well, I mean, even before I factored, let's back up a little bit. If I had plugged in the number 10 into the numerator, I would get 100 minus 50 minus 50, which is 100 minus 100, which is a 0. In the denominator, you have 10 minus 10, which is 0, which is what I mean by that indeterminate form, 0 over 0. Okay? All right, so when you have that form, the Calc 1 method was to factor and then remove common factors and hope the discontinuity issue kind of goes away. All right, with limits, we don't really care what happens exactly at that point 10. It's not continuity, right? There can be a hole there, but so long as the approach to 10 is clear, then we don't really care. Okay, so this function would not exist at x equals 10, but around x equals 10, it's all good. So we can compute the limit doing this algebraic transformation. So I'm going to substitute that in 10, and I get 10 plus 5 is 15. So hopefully you saw that in Calc 1. Okay, so that was the first type of form. And then the second type is kind of what I was talking about above, the infinity over infinity, and those 3 examples with the rational functions. Okay. The circling operation may be a little bit different if you took your calculus class with somebody other than me, but it works a lot in a lot of other circumstances. For example, even if you have exponentials, you can kind of pull this trick. So here I have the limit of 3 to the x plus 2 all over 3 to the x. And you can just look at, the high degree portions and take that limit. So quote unquote high degree portions, but really it's just the parts that are moving the fastest. This is just a limit of 1. And so the limit will equal 1. Okay. So a very powerful technique. I advise you to learn how to do that. Hopefully it's kind of obvious in the way I set it up. Okay, it turns out now that we have a powerful method for determining these 0 over 0 and infinity over infinity limits, and it's called L'Hopital's rule. L'Hopital is the name of the guy who was given credit for inventing this method, but it turned out he actually stole the method from somebody else. Anyways, this is used for 0 over 0 and then infinity over infinities, or negative infinity over positive infinity, or any variation with positives and negatives. And it basically just says that you could replace the limit of a ratio of functions that have this form by taking the individual derivatives of the functions. Okay? And then you could take that new resulting limit and have your answer. So it's pretty easy to apply. Let's look at number 4. Have the limit as x goes to 0 of the sine of 4x all over the sine of 3x. Okay? So when you're given these limits in the wild, you first kind of try to do a substitution. So you're hoping you just substitute and be done with it. So I plug in 0. I get sine of 0 is 0. And down below, sine of, it'll be 0 again. Right? So this is 0 over 0, and it has to be this form to apply this rule. It won't work if you just blindly apply it to everything. Okay. So anyways, here It's not the quotient rule, mind you. It's just you kind of cover up the denominator and just take the derivative of the top. So the derivative of sine 4x is cosine 4x times 4. And then cover up the top and take the derivative of the bottom. So the derivative of the bottom, cosine 3x times 3. And once you do that, you check it again. So you could do L'Hopital's multiple times. You could sit there and keep doing it as much as you want. And sometimes you have to do it a bunch of times. So here, but at every step you kind of have to recheck it and see if you could get away with your finding the answer. So anyways, cosine of 0 is just 1. So we can do it here and get out a number and we're good to go. Okay. Let's look at one where we have to do multiple L'Hopital's. So the limit as x goes to infinity of x cubed all over 5e to the x over 3. Again, I kind of judge the form. If I just look at x cubed, as x goes to infinity, x cubed is going to go to infinity. Likewise for 5e to the x over 3. So it's infinity over infinity form. I can apply L'Hopital's. So the numerator would be 3x squared. The denominator 5, the derivative of e to the x is e to the x. And then we have a chain rule. So the derivative of x over 3 is 1/3. Check the numerator and denominators again. They're both infinity forms. So do L'Hopital's again. That's perfectly legal. And you can kind of see what you're going to need to do. You're going to have to keep doing L'Hopital's until that numerator gets taken away, right? So if I do one more derivative, the numerator will just be 6. And then I'll have an L over infinity form, which will be 0. So the derivative of 6x is 6, and down below we got, oops, that should be a 3, right? So 5/27 e to the x over 3. Let's get rid of that complex fraction. In general, we don't like to write a complex fraction is like 1 over 1 over 2. And if you have a fraction in the denominator, you just multiply by its reciprocal. So in the numerator, then I'll have 6 times 27, whatever the heck that is. 162 all over 5 e to the x over 3, or you can just think of it as multiplying top and bottom by 27. And so here the form is some constant over something going to infinity, and that's 0. Okay. Something small over something getting bigger and bigger and bigger will just be 0. Okay. All right. Let's try number 8. So we have the limit as x goes to infinity of e to the 2x minus 5 over 3x. So again, first kind of identify the form. You'll have so the numerator is going to infinity. E to the 2x by itself is going to go to infinity. And if you're just subtracting 5 every time from every part of your table, it's not going to affect the fact that it's going to infinity. It'll still go. And it should be 3x in the denominator. So the denominator also is going to go to infinity. That's a linear function. So I could do L'Hopital's. So the numerator will have e to the 2x again, times 2 by the chain rule. And then the derivative of minus 5 is 0. All over the derivative of 3x is 3. Okay. So you have 2/3 times e to the 2x. If you're plugging in values for x, 10, 100, 1,000, 1,000,000, this thing is just going to go off to infinity. Okay, okay, great. Right, so these problems, these beginning problems are pretty easy, but there's 3 kind of variations on this idea. Okay, and you have to have all 3 of these methods kind of mastered before you can really move on into the real world. All right. So the 3 kind of other forms, we'll give them special names. They're other indeterminate forms, and the first type is infinity times 0. Okay, so you may be lulled into thinking, well, that's just equal to 0, but no, not so quick there, guy. You need to consider that there's a fight going on, right? So one part of your function is shooting off to infinity, one part is shooting off to 0, and you don't really know who's going to win that fight, all right? So you have to be careful and you have to use this form. And the way that will usually work is by rewriting this thing as, we want to rewrite it as kind of a 0 all over 1 all over infinity. Okay, so in that way, it'll turn out to be a 0 over 0 form. If that doesn't seem right, let me show you an example. Okay, if that makes no sense, let me show you an example. But the idea is it's this form. When you see this form, you're probably going to have to rewrite it as a fraction somehow. Okay, so let's look at number 9. Okay, so as usual, I kind of study the bits and pieces here. The x portion is going to go to infinity. And then the sine of 7 over x. In my margin here, the limit of the sine of 7 over x, you can move the limit inside the sine, and you have the limit of 7 over x. As x goes to infinity, that's L over infinity, which is 0. So you have sine of 0. And sine of 0 is 0. So that second part of our limit is just going to be 0. So this is the form that we're working with. So the remedy to this form is going to be to turn it into a fraction and then use L'Hopital's. Because as soon as you turn it into a fraction, you're going to get that 1 over infinity form, which will basically be L over infinity, which is your 0, and you'll have 0 over 0. Okay, so I'm going to leave that 0 thing in the top, and then I'm going to put 1 over x, so it'll cause a 1 over x in the denominator. And then if you reinvestigate, that numerator now is 0, and the denominator is, the limit of 1 over x. That will also be 0. Okay. So once you get it in this form, now you can apply L'Hopital's. And that's the common theme between all these other types. You're just kind of using algebra to manipulate it or transform it into something you could do L'Hopital's on. So in the numerator, I'll have cosine of 7 over x. If you have y equals 7 over x, it's 7x to the negative 1. So its derivative is negative 7x to the negative 2. And then that's all over the derivative of 1 over x is just negative x to the negative 2. Then you could simplify, so you have the limit, negative over negative is positive, the x to the negative 2's cancel, and you just have 7 cosine of 7 over x. And then I think we can evaluate that critter. So you can move the limit inside of the cosine function. The limit of 7 over x is 0, so you just have 7 cosine of 0. And that will just equal 7. Okay. So that's our first type. The next set are these weird exponential types where you have something in the denominator going in one direction and then the exponent is pulling it somewhere else. Every once in a while you have one that kind of looks like one of these but is determinate, so you can actually just compute the answer straight away. But in our work, they're all going to be indeterminate types, and you're going to have to pull these special tricks to kind of do it. So the one I chose is number 13. It's a little harder to deal with than some of the other ones maybe, but let's go ahead and take a look-see. So this is the limit as x goes to 1 from the right of the ln of x raised to the x minus 1 power. Now I will warn you, I do it a bit differently than what the book does. I think my way is more direct, but you can do the book's method if you so choose. All right, so anyways, what is the form? If you plug 1 into this expression, you get ln of 1, which is 0, and then that will be raised to the 1 minus 1 or 0th power. So this form is the 0 to the 0 power, and so we want to change it, somehow change it. And the way we do it is the way I do it is using inverses basically, if you have the ln of, well, let me write it a different way. If you have some base a to the x power, you can rewrite it as an exponential by saying, well, that's the same as e to the ln of a to the x, because e and the ln would cancel because they're inverses, and you'd just get a to the x. And then you could rewrite that as e to the x ln of a. So it effectively gets rid of the exponent issue. And then what you do is just move the limit into the exponent. Okay, so let's do that. I have the limit as x goes to 1 from the right, and then this will be e to the ln, and this gets a little nasty, but just hold on tight, ln of the ln to the x minus 1. Oops. And then I'm going to use the power rule of exponents to bring the x minus 1 down in front of the logarithm. And I'm also going to move this limit into the exponential. Okay, so hopefully I can do that all in one step and it's not going to blow your mind. I'll have e to the limit of x going to 1 from the right of x minus 1 times the ln of x. Okay, so at this point, what you're doing is just focusing in on this limit. You almost forget for the meantime that it's in an exponent. You just work in the exponent, okay? So your answer is going to be that thing, you know, e raised to whatever the heck that thing turns out to be. And that's kind of how the book does it. They basically just have you figure out the blue thing and at the end tack on the exponential part. Okay, but like I said, I think this way is more direct. Okay, so anyways, you investigate, right? What type of integral is that? Well, if you plug in 1, you'll have 1 minus 1, which is 0, and then times the ln of the ln of 1. The ln of 1 is 0, and so you have the ln of something going to 0. And if you're coming in from the right, so the ln of 1 from the right, you're going in this direction and you're getting values that are getting closer and closer to 0. The y values are diving down to 0. So you're taking like the ln of 0.1, ln of 0.001, ln of 0.001. So those y values, if you take their natural logs, you're going to have points down here going towards negative infinity. So this will be 0 times negative infinity, which is the previous form here, the first part A form. Okay, so you could have plus or minus infinity times 0. That's no big deal. So what do? Well, you turn it into a fraction, right? So you're going to have e to the limit as x goes to 1 from the right of the ln of the ln. I don't know why I wrote all that in red. Let me get carried away there. All right, so again, let's do it in black. E to the limit as x goes to 1 from the right of the ln of, so I'm going to leave this part in the numerator and then make a fraction with the other one. So in the original example I did that was of this form, I put the 0 portion in the bottom, I think, and then, no, I left the 0 up top, right? So here I'm leaving the infinity part up top. You could do it either way. But it's easier one way than it is the other. One way is going to be very hard, right? I think it's very hard. It may be impossible. I never really investigated, but okay. So anyways, here we are. And now that you have it in this form, that exponent is in the 0 over 0 form. So you can do L'Hopital's. Okay? So you have e to the limit as x goes to 1 from the right. So the numerator's derivative is 1 all over the guts, ln x, times the derivative of ln of x, which is 1 over x. That denominator, let's look at it in the margin for a sec. 1 over x minus 1 is the same as x minus 1 to the negative 1. So y prime would be negative x minus 1 to the negative 2. So let's rewrite that now in our limit. So I have negative 1 all over x minus 1 squared. And then I'm going to simplify it algebraically. So multiplying by reciprocal, and the numerator I have 1 all over x ln x, and that will be times negative x minus 1 squared all over 1. And then I'm going to have to reinvestigate again, right? So limit as x goes to 1 from the right of negative x minus 1 squared all over x ln x. Okay, so if you plug in 1, what do you get? What's the form again? Plug in 1, you'll get a 0 up top, and you get a 0 on the bottom. So you're going to do L'Hopital's again. So I have e to the limit as x goes to 1 from the right of, now it'll be negative 2 times x minus 1 all over, and the bottom I got to do a product rule. So leave x alone times the derivative of ln of x plus the derivative of x times ln x. Leave ln x alone. So the e to the limit as x goes to 1 from the right of negative 2 times x minus 1 all over x times 1 over x is 1 plus 1 times ln x is ln x. And then if you plug in 1 this time, it'll be a constant. So it'll just be 0. So in the numerator, negative 2 times 0 is 0. And the denominator, 1 plus ln of 1. ln of 1 is 0, so you get 1 plus 0, which is 1. And then 0 over 1 is just 0, so you get e to the 0, which is uno. All right. All right. Let's make the video quiz right here. Do number 10 for your video quiz. Hopefully that one's, well, maybe that won't be too hard. I don't know. Let's make it number 10. I'll kind of give you some hints here. So give me a second. Let me set it up first. So you have the limit as x goes to 0 from the right of 1 plus 1 all over x to the x. And you can see to the right the limit is going to be 1. Let me go ahead and compute it real quick, and then I'll maybe give you some hints. So I think this shouldn't be too hard. So I'll sort of set it up for you, at least in the beginning part. So you're going to turn it into the limit of the exponent e raised to the raised to the ln of 1 plus 1 all over x to the x, and then you do the power rule and bring the limit into the exponent. So this would be e to the limit as x goes to 0 from the right of x ln of, and what I did to make life a little bit easier was to kind of rewrite this as a fraction, just a single fraction with a common denominator, right? So in the first guy, you can turn that into x over x, and it would be x plus 1 all over x. So I could rewrite it as x plus 1 all over x, and then the form of this guy is going to be 0 times infinity. So here I'm going to rewrite it as e to the limit as x goes to 0 from the right of the ln of x plus 1 all over x divided by 1 over x. Okay, and at this point it's 0 over 0. And then you can do your L'Hopital's to it, and hopefully you'll get the answer from there. Okay, so the answer should be 1, but it's missing some steps. So again, please show all work or you will not get full credit. At the end of the day, it's 1. So I think the hard part is finding that derivative of the numerator. You may want to rewrite it as the ln of x plus 1 minus the ln of x, and then take its derivative, because as it sits right now, the derivative is going to be 1 over the fraction x plus 1 over x, and then times the derivative of that fraction. So then you have to tack on a quotient rule. So it may be easier to convert it first and then take the derivative. So rewrite it like this, then differentiate. Because at least in that case, it'll just be 1 over x plus 1 minus 1 over x. You still have some algebra to do. And then the denominator, you have to take the derivative of that as well. But, okay, so hopefully that won't be too big of an issue, and you can get it done. Anyways, the third type then is the infinity minus infinity or negative infinity plus infinity types. Just be careful. Types like infinity plus infinity are determinate. Those are actually just equal to infinity. So anyways, this one, there's a fight, right? One is going to positive infinity, and the other guy is dragging it in the other direction. So we need to worry about that. The limit as x goes to 2 from the right of 8 all over x squared minus 4 minus x all over x minus 2. Okay. So as usual, we kind of want to figure out what is the form. So that first guy, 8 all over x squared minus 4, the type is L over 0. So we need, is it plus or is it minus infinity? And again, the way I approach it, looking at the number line, I'm coming in from the right side, the positive numbers, and then I kind of just do a test value to see if it's positive or negative infinity. So if you plug in 2.1, you're going to get a positive over 2.1 squared is bigger than 4, so that will be positive over positive. So that part is positive infinity. Then for the other limit, let's just not consider the negative portion, and then of course up here when we write it, it'll be infinity minus whatever this limit is. So I'll have x all over x minus 2. Again, I consider the approach. I'm coming in from the right, coming in the 2 from the right, and then I do my little table. So the x value here is 2.1, so it'll be a positive over 2.1 minus 2 is positive, so it also will be positive infinity. So yeah, I have infinity minus infinity form. I need to do something to rectify that problem. And the algebraic transformation here is to take these two fractions and convert them into 1, all right? So be a little bit careful. In the denominator here, I want to factor. So I have x plus 2, x minus 2. And the other denominator, I just have the x minus 2. So to find a common denominator, I can just multiply the second guy by x plus 2 and top and bottom. Okay, so you turn the 1 fraction into 2, and you have 8. I'm going to go ahead and distribute this negative x. So minus x squared minus 2x all over x plus 2, x minus 2. Or if you'd rather x squared minus 4, we can just go ahead and rewrite it now. Because I think we're going to have to do the derivative of it, and it won't be easy to differentiate if you'd have to do a product rule otherwise. It's x squared minus 4. Right 2. So you're going to be substituting in 2 to see what type it is. So if you plug in 2 in the numerator, you have 8 minus 4 minus another 4, so that's just going to be a 0 form. And the numerator, in the bottom, it's 4 minus 4, again, 0 over 0, so you do L'Hopital's. So you have the limit as x goes to 2 from the right of derivative of 8 is 0, derivative of x squared, negative 2x, derivative negative 2x, negative 2. In the denominator, you'll have 2x. Do I need L'Hopital's again? So if I plug in, I'll have negative 2 times 2 is negative 4. No, I'm good now. Minus 2 all over 2 times 2 is 4. So that will be negative 6 fourths, which is negative 3 halves. Okay. For some reason in the software, they go and have you graph these things. I never graph anything. I know people like to graph things, but graphs can be wrong. Okay, and you don't want to learn that the hard way in real life. I just avoid them. I don't know. I'm old school. Maybe you could be more. They're more solid, but I mean, just for instance, if you do have something like even a Desmos won't pick up singularities. So, for instance, the fraction x minus 2 all over x minus 2 times x plus 2, right? there should be a discontinuity at 2. And if you look on the graph, there's no hole. This thing did not pick up that hole. Maybe if you zoom in, I don't know. I don't see it. Where is it? You would not know that was there. So what I'm trying to tell you is that graphs lie. Okay. I mean, you could try to kind of, where is it? It does kind of after a while. It's like, okay, 2's undefined. But if you didn't really know to look for it, you probably wouldn't have looked for it, right? So anyways, be careful is the long story short of it. They're probably just trying to get you to buy more calculators. Hey, if we put these problems in, they'll buy another calculator for us. I don't know. I don't know. It's my opinion. All right, so I'll leave it there. Thank you for watching as usual, and I will see you next time.